Conventional lithium-ion batteries rely on a liquid organic electrolyte to transport ions between electrodes. This volatile liquid poses severe flammability risks under thermal runaway conditions when internal short circuits occur or punctures breach the protective cell casing. Graphitic anodes in modern cells isolate lithium ions within carbon layers, limiting theoretical specific capacity to 372 mAh per gram. Exceeding this boundary requires replacing graphite with pure lithium metal, an impossible feat in liquid systems. Liquid electrolytes allow unconstrained microscopic lithium structures called dendrites to grow from the anode during rapid charging. These crystalline needles pierce the porous polymer separator, causing catastrophic short circuits, intense localized heating, and immediate thermal combustion. Solid-state technology completely eliminates the liquid solvent and volatile organic components. A solid material serves simultaneously as both the ion-conducting medium and the physical separator, separating the negative anode from the positive cathode.
Removing the traditional polyolefin separator frees physical space within the cell chassis. This structural consolidation directly yields higher volumetric energy density, enabling more active energy storage material to occupy the exact same total battery footprint. Unlike free movement in fluids, lithium ions within solid electrolytes migrate by hopping through distinct crystal lattice vacancies. Thermal energy vibrates the surrounding atoms, momentarily widening interstitial spaces and allowing ions to transition between stable coordination sites. Solid polymer electrolytes utilize long-chain macromolecules like polyethylene oxide, complexed with lithium salts. At elevated temperatures above 60 degrees Celsius, the amorphous regions of the polymer chain undergo segmental motion, conducting ions along the flexible backbone. Polymer electrolytes offer excellent mechanical flexibility and easy roll-to-roll manufacturing integration. However, their low ionic conductivity at room temperature necessitates auxiliary heating systems, reducing overall system-level energy efficiency in transport applications. Oxide-based ceramic electrolytes, such as lithium, lanthanum, zirconium oxide, exhibit exceptional chemical stability and high electrochemical voltage windows. These rigid crystalline structures withstand oxidative potentials exceeding 5 volts, enabling ultra-high voltage cathode chemistries. The extreme hardness of ceramic oxides introduces severe mechanical fragility. Manufacturing large, micrometer-thin ceramic sheets without structural microcracks remains highly challenging, requiring high-temperature sintering steps that complicate commercial high-volume production lines. Sulfide-based solid electrolytes, like lithium phosphorus sulfur compounds, possess outstanding room-temperature ionic conductivity, frequently surpassing 1 millisiemens per centimeter. Their mechanical softness allows excellent interfacial contact when compressed, bypassing the need for high-temperature processing. Sulfide electrolytes react violently with ambient moisture, producing toxic hydrogen sulfide gas. This chemical instability mandates specialized dry room manufacturing environments with dew points below -40 degrees Celsius, increasing industrial production infrastructure costs significantly.
Eliminating liquid allows the direct utilization of a pure lithium metal anode. Lithium metal provides a massive theoretical specific capacity of 3,860 mAh per gram, roughly 10 times greater than conventional graphite. Lithium metal exhibits the lowest electrochemical reduction potential of any element, measured at -3.04 volts versus the standard hydrogen electrode. This extreme value maximizes total cell voltage, unlocking unprecedented gravimetric energy density profiles. Solid-state batteries encounter high interfacial resistance, where the solid electrolyte meets solid active materials. Solid particles do not naturally wet surfaces like liquids do, creating microscopic gaps that restrict ion transport to a few point contacts. During charging, lithium ions deposit onto the anode, causing a substantial local volume expansion. Conversely, the cathode contracts as it evacuates ions, inducing severe mechanical stress across the solid-solid interfaces and prompting mechanical delamination over cycles.
To maintain uninterrupted solid-to-solid contact during volume alterations, cells require continuous external stack pressure. Heavy mechanical springs or containment frames must wrap the battery modules, adding parasitic weight that slightly offsets individual cell energy density gains. Advanced designs use anode-free configurations where no initial lithium metal foil is present. During the maiden charge, lithium ions migrate from the cathode and electroplate directly onto a bare copper current collector, maximizing manufacturing volumetric efficiency. Early hypotheses assumed rigid solid electrolytes would physically block dendrite propagation. Instead, high localized electronic conductivity within grain boundaries allows lithium nucleation inside the electrolyte, initiating microfractures that drive dendrite growth along structural defects. Dendrite penetration occurs when charging rates exceed a specific threshold, known as the critical current density. Surpassing this limit causes macroscopic void formation at the interface, forcing lithium to deposit unevenly into microscopic cracks until short-circuiting occurs. Solid-state cathodes cannot consist of pure active material alone. They must form a composite blend containing active cathode particles, solid electrolyte powder to ensure ionic pathways, and carbon additives to maintain adequate electronic conductivity throughout the layer. Ions moving through composite cathodes must navigate a highly tortuous pathway around non-conductive structural barriers. High tortuosity slows overall ion diffusion kinetics, restricting the maximum discharge rates and power performance characteristics of thick electrode configurations. Chemical incompatibility at the interfaces triggers spontaneous side reactions, forming a parasitic solid electrolyte interface layer. This growing boundary layer consumes active lithium ions and elevates internal impedance, accelerating long-term capacity degradation. To suppress interface reactions, manufacturers apply nanometer-thin protective coatings onto cathode particles using atomic layer deposition. Materials like lithium niobate isolate the active oxide particles from chemical reduction by aggressive sulfide solid electrolytes.
Emerging halide-based solid electrolytes, like lithium indium chloride, exhibit high oxidative stability combined with excellent water resistance compared to sulfides. Their unique mechanical and chemical profile provides a promising alternative for high-voltage cathode compatibility. Chemical potential differences between oxide cathodes and sulfide electrolytes generate a localized space charge layer. This phenomenon repels lithium ions at the interface, forming a high-resistance zone that severely diminishes high-rate charging capabilities. Co-sintering ceramic electrolytes with oxide cathodes require temperatures around 800 degrees Celsius. At these thermal thresholds, unwanted interdiffusion of transition metals occurs, generating non-conductive secondary phases that ruin cell performance entirely. To avoid high-temperature degradation, modern processes use cold pressing techniques or introduce transient liquid phases. These temporary liquids wet the solid boundaries before converting into solids via low-temperature chemical curing or rapid solvent evaporation. Conventional manufacturing utilizes toxic solvents like N-methylpyrrolidone to cast wet slurries. Solid-state production increasingly adopts dry electrode processing, mixing active materials with fibrillated polytetrafluoroethylene binders to form self-supporting electrode sheets mechanically. Under mechanical crushing or ballistic penetration, solid-state cells display superior safety compared to traditional batteries. The absence of volatile solvents prevents rapid gas pressure buildup and flash ignition, restricting thermal damage to the localized impact area. Solid-state batteries operate reliably across wide temperature ranges, remaining functional up to 100 degrees Celsius without electrolyte decomposition. This thermal resilience minimizes the necessity for heavy, complex liquid cooling loops within electric vehicle packs. Because solid electrolytes cannot leak, multiple individual cells can be stacked directly in series within a single pouch casing. This bipolar design eliminates external copper connectors, wiring harnesses, and redundant cell packaging, greatly elevating pack-level voltage.
Bipolar stacking shares a single metallic current collector foil between adjacent cells, serving as the anode substrate on one side and the cathode substrate on the reverse. This architecture trims inactive structural mass and significantly maximizes system density. Solid electrolytes exhibit negligible electronic conductivity, reducing internal parasitic leakage currents to near zero. Consequently, solid-state cells maintain their charge over years of storage with minimal self-discharge, outperforming liquid chemistry shelf life profiles. While energy density excels, solid-state cells struggle with extreme high-power delivery. The sluggish diffusion kinetics of ions through solid matrices limits maximum current output, making early generations highly suited for steady energy discharge rather than sports acceleration. Mitigating mechanical degradation requires solid materials with specific mechanical creep and yield strengths. The electrolyte must deform plastically under stack pressure to fill emerging voids without cracking or permitting lithium dendrite infiltration through grain boundaries. Crystalline oxide electrolytes possess microscopic grain boundaries with distinct chemical compositions from the bulk crystal. Engineering these boundaries via dopants like tantalum or niobium reduces localized electronic conductivity, successfully suppressing internal lithium plating paths. To eliminate grain boundaries entirely, researchers synthesize amorphous glass solid electrolytes. Glassy materials like lithium phosphorus oxynitride offer uniform isotropic ionic conductivity and completely lack structured boundaries, providing excellent resistance to localized dendrite penetration. Environmental life cycle assessments indicate solid-state architectures can lower battery carbon footprints by up to 39%. Eliminating graphite reduces mining burdens, though high lithium requirements per kilowatt-hour necessitate expanded sustainable mineral extraction strategies. Recycling solid-state batteries demands distinct hydrometallurgical or pyrometallurgical separation processes. Because ceramics and sulfides do not dissolve like standard polymer separators, automated mechanical milling must isolate the solid electrolyte fractions before chemical leaching stages. To accelerate market entry, initial commercial implementations utilize semi-solid or hybrid designs. These systems introduce minimal amounts of targeted liquid electrolyte at the cathode interface to resolve wetting issues while maintaining the safety benefits of a solid separator. Capital expenditure for early solid-state production remains high due to low yields and specialized dry room requirements. Cost parity with conventional lithium-ion cells depends heavily on scaling automated high-speed web handling equipment for brittle materials. Beyond transportation, the non-flammable nature of solid-state chemistry makes it ideal for stationary grid-scale energy storage. Large-scale installations can be packed densely without massive fire suppression systems, minimizing land use footprint requirements. High gravimetric energy density unlocks electrification possibilities for regional aviation and unmanned aerial vehicles. Weight savings from eliminated cooling infrastructure and compact cell packing allow electric flight profiles previously deemed impossible with heavy liquid batteries. Solid-state chemistry fundamentally redefines electrochemical storage paradigms. Overcoming interfacial mechanics and optimizing mass production will phase out volatile liquid systems, establishing a safe and highly energy-dense foundation for global zero-emission infrastructure.